Hello everyone, welcome to our session on underfitting and overfitting. These are extremely important issues for the machine learning engineer as they can make or break a model. So in this session, we will try and understand the following issues. What do these terms mean? How are they bad? And what can we do about it? So all data has information and noise. Now information is repeatable, but noise is not. So in a model, we are trying to catch all the information, but none of the noise. Let's consider a model that captures the relationship shown in this plot. So we're going to try and make a model to capture the relationship that we see here. We'll start by fitting a line. Now this can be easily done using a standard linear regression. But we are not happy with the model as it seems to be missing too many points. This is a situation where the model is too simple to be able to accurately reflect the essence of the underlying data. So we increase the complexity of our model. Now this can be done by including exponents, for example, and the resulting outcome may be represented as this curved line. The model is starting to look better as the curve is now reaching closer to more points than the straight line was. We like the process, so we continue to add more complexity to the model. We make it more and more complex, and as a result, our line starts to get more and more wriggly, and after a while it looks something like this. Perfect. Now the model has managed to touch all the points. We are happy with the look as the model has captured all the data. However, such a model is going to face major problems when new data is presented to it. In fact, the middle model would have performed much better with the new data. So our problem is a model that managed to fit every single point on the training data actually fares badly when new data is shown to it. So every new point indicated by green is off the line. Now the question is, why did this happen and how can we prevent it? So every data set is a sample of the universe of data that we are interested in, and we can fit multiple models to it. A dataset would contain information about the universe it comes from, but it also contains noise and random artifacts. So a good model will include the information but leave out the noise. That means a good model will effectively capture the shape of the data that our dataset is representing. So how do we know how much complexity is enough? Well, we can plot a graph of model complexity and model error to see the relationship. When this graph is plotted for training data, the trend is monotonically downwards. As the model complexity increases, the error keeps going down. At the extreme right side, we have a situation where the model has memorized every single data point in the training set. Now we are going to test the model using the test data, which has been kept separately and which the model has not yet seen. And we are going to plot the performance on the same graph. So this is what we get. There's an initial phase where the performance of the model improves as indicated by the declining error rate. We're talking of the red line now. Now this is the phase when adding complexity to the model is helping our model, as the model is now learning actual information from the data. However, as we continue to increase model complexity, there comes a point when the model performance starts to decrease again. And the line starts to go up again, reflected by our curve turning upwards. This marks the point when the model has successfully learnt all the information, and from now on it is starting to capture noise. So this turn is the place where the model is fitted the best. This is the best model fit we can have. So our aim is to target the middle area where the model error for the test data is at its minimum. Now to summarize, a model that fails to capture the nature of the relationship will perform poorly on training and test data both. This is called underfitting. We have not really captured the essence. A model that tries to adapt too much to the data will end up modeling the noise as well. This is called overfitting, and this leads to poor performance in a real world situation. It can be prevented by using a simpler model and by using techniques such as cross-validation when we are keeping a separate bit of data which the model doesn't see so that we can compare it. So that's it for today. Thank you for watching.